Hey students, welcome to the second lecture of Linear Algebra 1. So last time we talked about linear systems, and today we want to introduce matrices and vectors, and with these we want to rewrite these linear systems and then see how we solve these linear systems by using these new notations. So recall that last time a linear system was given by a finite collection of linear equations like here. So here we have two equations with two variables, and then we learned how to solve such a linear system by using these elementary row operations, which were given by adding one row to another or multiplying a row with some factor. And today we want to rewrite these by using matrices and vectors. And in this example here, for example, we can write the left-hand side of this linear system as a product of a matrix with a vector. So for example here, we will see that we can write this like this. So this here is a 2 by 2 matrix, and we have a vector here of size 2. So if you multiply this out, this gives a vector of size 2, which has exactly these entries of these equations on the left-hand side. And on the right-hand side, this we can also interpret as a vector of size 2. So here, solving this linear equation means that we want to find a vector such that if we multiply this vector with this matrix, that we get this vector here. And then we will introduce the so-called augmented matrix of the linear equation, which in this case just means that we write this vector here as an additional column. So we will rewrite this linear system like this. So this will be a 2 by 3 matrix. And then these row operation we introduced last time, we will introduce for matrices. And then we will do this row operation on this matrix here. And in the end we will have, we will want to find a matrix on a certain form, which will be the row reduced echelon form, which already appeared in the homework for linear systems. And then using this row reduced echelon form, we will introduce the notion of a rank of a matrix, and then comparing the rank of these augmented matrices with the original matrix will then tell us something about the solutions of these linear systems. Okay, but let's start at the beginning with the definition. So what is a matrix? So some of you maybe saw these already in high school. And a matrix is just an array. So an m times n matrix is given by some array of numbers, where the first number here is the number of rows, and the second number is the number of columns. So in this case here we have m rows and n columns, and we have these numbers. So we have m times n numbers aij, and which are real numbers. And then we write the matrix A is given by the array of these numbers. And here in this aij, the first entry always indicates the row, and the second the column. So for example, if I have A is 1, 2, 3, 4, then in this case the entry A to 1 is 3, because it's the entry in the second row and the first column. And another notation, instead of writing it like this, is that we just write it like this. So we say it's a collection of numbers, aij, where this I runs from 1 to m, and this j runs from 1 to n. And sometimes we will leave out this part here and just say we have a matrix A. And this we say when we, for example, already know what the size of this A is, and then in this case it's clear what m and n are. And the set of all matrices with m rows and n columns will be denoted by R m times n. And a special case of a matrix is a vector, or more precisely what we will call a vector is usually called a column vector. So in some linear algebra books they consider row vectors, but usually when we talk about a vector we just mean a matrix with exactly one column. So a vector of size n is just an n times n matrix, which looks like this. So it's exactly the same notation as here. And the set of vectors of size n will be denoted by Rn. Okay, so, and vectors maybe you also saw in school. So for example, if the size is 2, we can draw these vectors in the plane. So this is the R2 now here. And for example, this is a vector of size 2 with entry 1, 2. And usually here, this axis is the x-axis and this is the y-axis. So this just means this is here. Maybe I don't write it down, but in this direction usually we mean the first entry and here the second. So for example, this vector here goes 1 to the right and 2 up. And this vector here, u, goes 2 to the right and -1 up, so it goes 1 down. And then what we can do with vectors is we can also add them. So in this case, what we mean by, for example, u plus v would be that we just attach this vector u to this vector v here. So for example, if I copy this vector here and I put it there, then of course I get the same as I would get if I take this vector and, oops, maybe I should have just written it, put it there. So we get to the same point here, and this will be exactly u plus v here. And so what are the entries of this? So this here is u, 2 minus 1, plus v, which is 1, 2. And what we do is we just add component-wise. So here it's 3 and 1, because it's -1 plus 2. And here we see that, so if this is the red vector, this vector here, the sum of u and v is exactly this. We go 3 to the right and 1 up. So adding vectors just means adding these entries component-wise, and also it makes just sense to add vectors of the same size. And this is defined more generally for matrices. So and vectors are just a special case of matrices. So in general, if we have two matrices, A and B, which are both of the same size, so here they are m times n matrices, and that's why we also leave out this information here, because we know that both of them have this size. So this I and j here both runs from 1 to m and from 1 to n. And then the sum of these two matrices is just the new matrix, which also has this size m times n. And the entry of this matrix A plus B is just given by component-wise adding these entries of A and B. And then there's also a scalar multiplication. So for this we take a real number lambda, which is also called a scalar. And then this notation lambda times A, so a number times a matrix, this just means that each entry gets multiplied by this lambda. And so simple example, 1, 2, 3, 4 plus 0, 1, minus 1, 0, for example. The sum of these two matrices is just I add component-wise these numbers. And then also, so we don't really define the subtraction of matrices, but what we mean by this expression A minus B, that minus B just means -1 times B. So we multiply each entry of the matrix B with -1, and then we add this to the matrix A. So this then just in the end just means that the entries of A, for each entry of A, we subtract the entries of B. And since vectors are just special cases of matrices, so here again written for vectors, so if I have two vectors of size n, then I can define the sum, which just means that each entry I add these entries, and multiplying with a lambda just means I multiply each entry with a lambda. And this picture here, if I multiply a vector with a number, this just means I stretch this vector by this factor lambda. Okay, so this is the addition of matrices and of vectors. And what we want to define now is the product of a matrix and a vector. So as we saw at the beginning, these linear systems will be given by multiplying a matrix with a vector. And for this, we take an m by n matrix A, and then we take a vector of size n. So this vector, the size of this vector needs to be the number of columns of this matrix, otherwise the product A times V is not defined. So here this is a matrix A, this is a vector V, and the product of these matrix and vector gives a new vector. So what we do is we multiply an m times n matrix with a vector of size n, and the product will be a vector, and this vector will have the size which corresponds to the rows of the matrix A. So this will give a vector of size m. And how is this defined? Well, what you do is you take this vector and you somehow, so that's how I always think about this, I put this on top. So here this v1 will get multiplied with each entry here. So I take this vector and put it here on top. And to get the first entry here, I multiply a11 with v1, a12 with v2, and so on, and then in the end I multiply vn with a1n. And then to get the second entry here, I take this vector and multiply it with the second row here to get this. So the first entry of the second row gets multiplied with this, then this with this, and so on. And then it's also clear why in the end we get a vector of size m, because we do this for each row here in this matrix. So for example, if we have this product here, so here we have the matrix A, which in this case is a 3 by 2 matrix, and here we have this vector V, which is a vector of size 2. In this case we should get a vector of size 3, and the entries are given by, well, the first entry is I take the 1 times minus 1 plus 4 times 3. So this is 12 minus 1, so this is 11. And then the second entry is 2 times minus 1 plus 5 times 3. Well, 15 minus 2, so it's 13. And then 3 times minus 1 plus 6 times 3, so 18 minus 3 is 15. And this is then the result of this product of this matrix and this vector. And these multiplications of matrices with vectors, and we will generalize this later. Later we will introduce the product of two matrices. But for now we just consider multiplying a matrix with a vector. And these products, they satisfy certain rules, which are quite similar to the rules which are satisfied by real numbers. And so, for example, if I have a matrix of size m times n, and I have two vectors of size n, and a scalar lambda, then we have these two statements that if I first add these two vectors, so I can add two vectors of the same size, which gives a new vector of size n, and if I multiply it then with the matrix A, this is the same as first multiplying the vector x with the matrix A, which gives a vector of size m, and then I multiply A with the vector y, which also gives a vector of size m, and these two vectors of size m I can also multiply. So here in this result is on both sides a vector of size m. And the statement is it doesn't matter what you do first, so we have this equation here. And also if I multiply a vector first by a scalar and then multiply with a matrix, is the same as first multiplying a vector with this matrix and then in the end multiply this vector with the vector lambda. And this you will show in your, well, it's not hard to show, it follows directly actually by this definition. It's always just a question on how to write it down precisely. Just try to write down what this actually means by definition. So you start with two vectors, x and y, and x has entries x1 up to xn, and y has some entries y1 up to yn, and then write down what this x plus y means. This gives a new vector, and this has certain entries, and then multiplying with a matrix using this definition here gives a new vector, and then compare it with the definition of this entry here. So this is homework 2, exercise 1 or 2, I think. Okay, but now we want to come to this linear systems and matrices and vectors. So for this we do now example number 4. So now we consider this 2 by 3 matrix A and this vector B of size 2. And now we want to ask the following question. We want to find all x vectors of size 3, such that if I multiply this matrix with this vector x of size 3, we get this vector B. And so what does this mean? So what is AX? So by definition, so this is a matrix, this one here, and we want to multiply it with the vector x1, x2, x3. And by definition, this is x1 plus 2 times x2 plus 3 times x3. And the second entry here is x1 plus x2 plus 4 times x3. So this is a times x, so this is a vector of size 2, and we want this to be the same as 1, 2, because this is B. But this is equivalent, so these two vectors are the same if each entry is the same. So from this equation here we see we get two equations, namely the first equation is just whether this entry should be 1, and the second is that this entry should be 2. So this gives a linear system. So from this equation here, matrix times vector equals vector gives a linear system. So if you can answer this question, this is equivalent of answering this question. And therefore this is why we also call this here we also call a linear system in the following. Even though we defined this to be a finite collection of linear equation, but here we see that if you multiply this out and you want to have this equation, then this is actually equivalent to a linear system. So an equation like this we will also call a linear system. And now last time what we did to solve this linear system, we applied row operations. So how did we do this? Well, in this case we wanted to get rid of this x1, so we took -1 times this here, the first equation, and added to the second, so the first stays the same. Oh, here's also a 2 missing. So this is still 1. And here we have no x1 anymore, and we subtract the -2 from there, so this is a minus. And here's also the 2 missing. x2 and 3 minus, so this is still x3. And here 2 minus 1 is 1. And now we can do two things. So either we could first multiply, so the algorithm we described last time would first multiply this by -1. But here we can also first maybe get rid of this x2 here. So we can take 2 times this and add it there. So what we get is x1 and then no more x2. And we add 2 to the 3, so we get 5x3 equals 3, because it's 2 plus 1. And here we still have -x2 plus x3 equals 1. And then in the end we can multiply this with -1. And we get the final form from which we can read off the solutions of this linear system. Because last time we learned that at this stage here now we say that these two are called the pivot variables, and x3 in this case here is a free variable. So the solutions in this case can be obtained by setting x3 to an arbitrary number, saying x3 equals t, and then x1 and x2 are determined by this t. So if this is t, then for example x1 is 3 minus 5 times t. So the solutions here is x1 is 3 minus 5 times t. So t is now an arbitrary real number. x2, the second pivot variable, is just minus 1 plus t. And x3, because x3 is a free variable, is just our t. So here we see these are our solutions to our to all of these linear systems. But this is also now gives the entries of the vector which satisfies this equation here. So if I multiply this matrix with the vector x, which has these entries for arbitrary t, then I will always get this vector b. So using now this vector description, so recall our vector x was given by this. So now we can, what does this mean? The first entry is 3 minus 5t. The second entry is minus 1 plus t. And the last one is 0 plus t. And this we can rewrite now by using the addition and the scalar multiplication of vectors, because this is the same as saying we take the vector 3 minus 1, 0, and we add t times the vector minus 5, 1, 1. Because this here is now the scalar multiplication. So sometimes we write a dot and sometimes you can also leave it out. But so this just means that we multiply each entry here with t, and then adding just means we add component wise. So we get exactly this vector when we calculate this here. And now we can interpret this. So what does this mean? So the vector x such that ax equals b are all these vectors where I take this vector plus a multiple of this vector. And this one can visualize. So let's get this here. So for example, we can now plug in different t's. So let's say, for example, if t equals 0, then this x is just 3 minus 1, 0. So here in this three-dimensional space, so this here is now R3. And we now want to plot all possible solutions in R3. And one of them is given by this 3 minus 1, 0. So here on the x1 axis we go 3 to 3. And on the x2 axis we go minus 1. And x3 axis we go 0. So here this point is one possible solution. But now we can also take, let's say, t equals 1. In this case, this x is 3 minus 5, so minus 2. And minus 1 plus 1 is 0, and 0 plus 1 is 1. So here this point is minus 2 on the x-axis, 0 on the x2 axis, and it goes 1 in the x3 axis, so here. So this point here. And in the end, all possible solutions here, so if you would plug in now different t's, what you will see is that all possible solutions are now given by a line which goes through these 2 points. So these are all solutions. So this gives somehow a geometric interpretation of the possible solutions. So all vectors on this green line here now satisfy the property that a times x equals b, or equals 1, 2 in this case. Okay. And so what we want to do now is here, when solving this linear equation, of solving this original problem here, we use this notation of linear equations again. But actually we don't need to write these x's the whole time. It's what we basically are just interested in are in these coefficients. So therefore we will also use a matrix notation to solve these linear equations. And for this, as I said at the beginning, we want to introduce the so-called augmented matrix of a linear system like this, where we just care about the entries of A and B. And this is the next thing we want to introduce. So if I have a matrix A, an m by n matrix, and a vector B, then this matrix here, where here I just write the matrix A, I add this vector B as a column, and I write this line here. This will be called the augmented matrix of this linear system AX equals B. And this itself is also just a matrix of size m times n plus 1, because here we added one column. And this line here doesn't really have any real meaning. So this is really just a usual matrix where we didn't define what this line means, but it just helps to indicate which part is the left-hand side and the right-hand side of this original linear system. So in the example before, we saw what is this? In the example before, we had this augmented matrix where A was 1, 2, 3, 1, 1, 4, and here on this part we had this vector B 1, 2. And then solving this linear equation, this linear system AX equals B, what we want to do is we just want to apply row operations now on this matrix here. And this is what we introduce now. So these are exactly the same row operations we introduced last time, but for linear systems. But now we will just, in the word linear system, or linear equation, or the word equation will get replaced by just a row. So the following operations on a matrix are called elementary row operations. So R1 just means we add a multiple of one row to another row. Multiplying a row with a non-zero number is called R2, and interchanging two rows is called R3. And these are exactly the same as before, because here R3, for example, before was changing the order of two equations. And yes, so and after this, so what we want to do is we start with a linear system. So we start with a linear system, then we write down the augmented matrix, and then we want to apply these row operations to come to a certain point, which then correspond to this form here. And for this, we first introduce another notation, which says that if I apply an elementary row operation to a matrix A, I get a new matrix, and we say that these two matrices are row equivalent. So if I have two matrices A and B, and then they are called row equivalent, if I can obtain this matrix B from this matrix A by applying certain elementary row operations. And then the notation we use is this thing here, A is row equivalent to B. So therefore, we will now use the following notation. So if I start with the linear system AX equals B, then I want to solve this, and first what I do is I write down the augmented matrix, and then I apply these equivalent row operations, and I use the same notation. I say what was the first step. In this case, we took this first row and subtracted it from there, so this is row operations R1. And now instead of writing equivalent, which I cannot write now because so we use this symbol here, which meant equivalent, because both sides here are statements. What we want to use now is this new notion of row equivalent. So applying this row operation gives a new matrix, which is row equivalent, so I just write this row equivalent. And in this case, the matrix I get is this. So now I subtract the first row from the second. So I get 0, -1, 1, 1. And here we do the same as before. We take this row and add it 2 times there. And then I get again a row equivalent matrix. 1, 0, 5, 3, 1, 0, minus 1, 1. And so this is also row operation R1. But this you don't need to write. It's just for now. And this here now I use row operation R2. I multiply the second row with this. And I get a new matrix with which is row equivalent given by this. And this is the final form we want. So don't write that these two matrices are equivalent, because this doesn't make sense. So this symbol here is just for statements, like an equation, and an equation is a statement. But here these are matrices, so these are not statements, but we can say that this matrix is row equivalent to this matrix. So if this A is and B, then A is row equivalent to B, because from A to B I can go by using this row operation R1. And also notice that if A is row equivalent to B, then B is also row equivalent to A, because I can also go from B to A by using a elementary row operation, because as we saw last time, these elementary row operations are invertible. So here I can go from there to there by adding the first row 1 times to the second. So we can go in both directions, and therefore one says that this row equivalence, so this is actually what people call an equivalence relation, and this is symmetric. So if something is equivalent to something else, then this something else is also equivalent to this. Okay, and now we want to talk about this final form, which we introduce in the homework for linear systems, which we called row-reduced echelon form, and the same we want to do for our augmented matrices, or in general for matrices, not necessarily for augmented matrices. But also first the statement is that, as I said, we can invert these elementary row operations. So the first statement we have here is that if I have two matrices A and B, and I have two vectors B and C, then if this augmented matrix AB is row equivalent to the matrix BC, this means that this linear system AX equals B and the linear system BX equals C have the same solutions. So this in our example here just means, for example, here we start with A and B, and for example here in the end we have B and C. So C is now the vector 3, minus 1, and B is this matrix. We see that these two matrices are row equivalent, and we also see that the corresponding linear systems have the same solutions, because we can go in these both directions. Okay, but now the final form, the row-reduced echelon form, and it's really similar to the definition we did for linear systems in the homework. So we say that a matrix, so usually this matrix will be the augmented matrix. So, but now in general for any matrix, we can say what it means for this matrix to be on row-reduced echelon form. This means that the first non-zero element on each row is 1. If there are any, it could be that there are no non-zero elements, for example the zero matrix where everything is 0. Then the second statement, if there's a leading 1 in some row, then all the rows above have some 1 on the left. So maybe for example here, let's take these two examples. Perfect. Because this is a picture, sorry. So let's take this and this. So here we have two matrices. So these are two matrices. These are both 2 by 4 matrices. And this matrix here is on row-reduced echelon form. It satisfies this condition. But for example, this here is not on row-reduced echelon form. And why is this not on row-reduced echelon form? Because we also have this third condition here, that if aij is the first non-zero element in some row I, so for example here, this is a, it's in the second row and the second column. This is the first non-zero entry in row 2, so row I, and then there are no other non-zero elements in this column. So there are no non-zero elements here, so there's just this 0 here. But for example here, this A2, 1 is the first non-zero element in the second row, and it's in the first column, but here in the first column there's also still a non-zero element. So this here is not in row-reduced echelon form. So here for row-reduced echelon form we use the abbreviation RREF, but this here is in row-reduced echelon form. And the algorithm we introduced last time, or the strategy, this Gaussian elimination process, this is the same for these here. So to get a row-reduced echelon form from some matrix, so if we start like this, then we use the same strategy as before. So we will first do this downward step and then use this upward step. And then starting with this matrix here, we can do some row operations, and then in the end we see that these two matrices are row equivalent. So therefore this matrix here, which is not in row-reduced echelon form, is row equivalent to this matrix here in row-reduced echelon form. And this is true in general, or it's even, there's a stronger statement, namely that we have the following, that any matrix A is row equivalent to a unique, so there's just one. So if I start with an arbitrary matrix and I apply these elementary row operations, and in the end I get some matrix in row-reduced echelon form, then this matrix is unique. So it wouldn't be possible to use other row operations and end up with another matrix which is different to this matrix B and which is also in row-reduced echelon form. And therefore we can introduce this notation here, that if I start with a matrix A, then there's a unique matrix B which is on row-reduced echelon form, and then we use this notation that this B is this row-reduced echelon form of this matrix A. And we will not prove this precisely, but what you would need to show is that if you have two things on row-reduced echelon form and which are different, then you cannot go from one matrix to the other by using these elementary row operations. Okay. And so what is now the strategy to solve a linear system? So if I want to solve a linear system like this, what I do, I consider the augmented matrix A, B, and then I will do elementary row operations, and in the end I will have something on row-reduced echelon form, and this will be the row-reduced echelon form of this matrix AB. So it will be the row-reduced echelon form of an augmented matrix. So don't get confused now with, this is also an A, but in this case here, this whole thing here is the matrix A. And then we want to read off of this matrix here. So let's call this matrix BC. So it will also be a matrix where on the last column is some column which we call C, and then there's some matrix here. And from this we now want to read off the solutions of this original linear system. So, but first let's think about how in general a matrix on row-reduced echelon form can look like. So in general we have the following shape. So again, if I start with some matrix, augmented matrix AB, and then I do some row operations and come up with the matrix on row reduced echelon form, and this can have the following form. So in the first row, this could start with some zeros, and at some point I will have the first non-zero element, which needs to be 1. So maybe let's copy the definition here. So because of the first condition here, the first non-zero element in each row is 1. So here we have the first non-zero element in the first row. And then there can also be nothing else in this row here. But everything here is 0 anyway. But then there can be something in the first row. And then at some point, there will be the first non-zero element in the second row. But then there's nothing here in the same column. But then there can be something here in the first and the second row, until to the point where in the third row there's the first non-zero element, but there are no non-zero elements here. And also what I forgot to say, which was written here, that the first non-zero element in a matrix of row reduced echelon form is, like before, is called pivot element. Oh, I want orange. So here, these are the pivot elements. And then at some point, we have the last row where there's something. So here in the end, everything needs to be 0. And now there comes the last column here, which is this vector C. And there can be now two things. So either this column here in this row has a non-zero entry, lambda. Then because everything is in row reduced echelon form, this also needs to be 1. Or it could be that there's no entry here. So this is just 0, and then just these elements are the pivot elements. But it could be that this lambda is 1, and then we have an additional pivot element there. And now to read off the possible solutions of this linear system Ax equals b, we bring it to row reduced echelon form, and then this gives a matrix B and a vector C. And then looking at this thing here, we can decide what are the solutions of the original system. So this is now, so we want to read off the solutions. And there can be now different cases. So it could be that this lambda is 1, but if this lambda here is 1, then this row here corresponds to the equation that 0 equals 1, and this has no solutions. So if this lambda is 1, then we actually don't have any solution. So in other words, this vector C contains a pivot element, then we have no solutions. But then we have the case lambda is 0, and there are two special cases. So if lambda is 0, so there's nothing here, we just have this part. And so now it could be, we can ask ourselves how many solutions are there. So first of all, there are solutions, because these pivot elements correspond to these pivot variables we had before, and the places in between corresponds to the free variables. So if there are some free variables, then we saw that we always have infinitely many solutions because we can choose them freely. But if there are no free variables, so if we are in each column we have a pivot element, which means that every variable is a pivot variable, then we have a unique solution. And this unique solution is given by this entry here. So this C prime here is this vector here. So if so the statement is if every column of B contains a pivot element, then we have the unique solution C equals this C prime. So for example, if I have let's do it like this, 2, 3, 0. This is the case now, like so this is B, this is C, and C prime in this case is 2, 3. So C in this case is 2, 3, 0. And if we think about the corresponding solution equations here, then this row reads x1 equals 2, and this row reads x2 equals 3. And therefore the solution is exactly given by what is left here on the right hand side. So this is why in this case we have a unique solution. So maybe this I want purple. Unique solution. And this unique solution is given by the entries here. But then it could also be the case that even so when this lambda is 0, it could be that there are still these spaces in between, meaning not every column of B contains a pivot element. So in this case we have infinitely many. So if some columns of B do not contain pivot elements, then we have infinitely many solutions. Because then we have free variables. So for example, if I would have here, let's say an additional column, let's say with, oops, what was this? With 8 minus 5, then we have just the first two columns of B contain a pivot element, and then we have infinitely many solutions. We can say that x3 in this case is free and arbitrary, and then x1 is 2 minus 8 times t, x2 is 3 plus 5 times t, and x3 equals t. Okay, so it's really important in the end. What really matters is the pivot elements. So we are interested in where are the pivot elements in B, how many pivot elements are there. So if the maximum number of pivot elements for this part here is of course, so B is an m by n matrix, so this here is n. So if every column contains a pivot element, so the maximum number of pivot elements is n. And now the question is if this whole matrix here has more pivot elements. So if there's a 1 here, then this whole matrix has one more pivot element here. So therefore the number of pivot elements in everything is bigger than here. Then this means we have no solutions. If there's no pivot element here, then the pivot elements of this whole thing is the same as the pivot elements here. And in this case, if the number of pivot elements in this matrix B equals n, then there's a unique solution. And if the number of pivot elements is smaller than n, then there are infinitely many solutions. And because the number of pivot elements in a matrix is such an important number, this becomes the name, and this is called the rank of a matrix. So if I have an arbitrary matrix A, sometimes it's an augmented matrix, but sometimes it's just a usual matrix, then the rank of this matrix is the number of pivot elements in its row-reduced echelon form. So to calculate the rank of a matrix, of an arbitrary matrix, you first need to bring it into row-reduced echelon form, and then in this row-reduced echelon form you can count the number of pivot elements, meaning just the number of ones starting in these rows, and this is called the rank. And this then has this nice interpretation. So let me bring this up. As I said before, that if I'm interested in the solutions of this linear system, Ax equals b, then the statement that if the rank of A, the augmented matrix AB, is bigger than the rank of A, so this means that there is an additional pivot element here in the row-reduced echelon form of this, then there are no solutions. But if the rank of the augmented matrix equals the rank of A, so the rank of A is the same as the rank of B, because B here, one should also say B in this case is also the row-reduced echelon form of A, and this whole thing is the row-reduced echelon form of AB, and the rank of B is the same as the rank of A, and if the rank of this is smaller than the rank of this, is the same, sorry, then there are solutions, and if the rank of this matrix B is exactly the number of columns, then there are unique solutions. Then there's just one unique solution. So this is this case here. But if the rank of the augmented matrix is the same as this, but everything is smaller than the number of columns of B, then there are some spaces in between, so there are free variables, and this means we have infinitely many solutions. Okay, and that's all for today. So in the homework 2, you will calculate you will give some examples of matrices with a certain rank, and you will also calculate the matrix of a 2x2 matrix in general. And next time we will start talking about maps to prepare linear maps, and linear maps will be given basically by multiplication by matrices, and then we will see, so you will prove in the homework that, not this one here, you will prove in the homework that matrix multiplication satisfies these two properties, and these two properties will be used to define linear maps in general. But this we will do next time, so see you then.